later okay, awesome. The recording started. Great. So today we're gonna present robust and reproducible AI statistical foundations for machine learning in medical imaging. There's the QR code on the slides. You also have the link there. Please feel free to check the GitHub repository we have put together. We will go through the codes, and on the side we'll have some slides to be shared with you. These slides are already there, so basically you have access to everything. Dr. Terrell, could you go to the next slide?
Just give me a sec, Ernest. Sorry. My presentation. There we go. My apologies.
Awesome. So I'm Ernest. I'm a postdoctoral fellow at University of Toronto, also Dalhousie University, senior data analyst at Sick Kids Hospital, ambassador in AI for healthcare at NVIDIA, also a PhD license holder in software engineering. The QR code leads you to my LinkedIn. Happy to be connected and chat more after the session. Dr. Terrell, please. With me is Dr. Pascal Triol.
You want me to?
Yeah, sure. You can go ahead. A fantastic
Sure.
mentor of mine.
So, yeah.
Please take the floor.
So my apologies. I'm just trying to get all of this sorted out on our screens because we're going to be on here for a couple, like 3 hours here. So I wanted to make sure everything is ready for you guys. Thank you, Ernest. First and foremost, what I'm trying to do is get the list of participants in the chat ready. So as you can imagine, I've been teaching in a hybrid and online since COVID. So it's nothing new to me, but it's always challenging to make sure that we don't lose track of the participants. So let me just start first by saying, first of all, thank you very much for hosting us. We really appreciate it. We absolutely appreciate being able to deliver this virtually. It just made sense for us for our schedules, and we appreciate that. And from your perspective as an audience, please feel free to use the chat as much as you would like. That's why I wanted to set this up correctly. I have the chat open here, and I'll be keeping an eye on it, and I'm sure Ernest will as well. So feel free to interact however you would like. You can either blurt out your questions or you can write them in the chat. We're absolutely okay with that. And for instance, we already have a question from, I think, Serene. Is that how you pronounce your name? Please unmute and let's test. Oh, allow to talk. There you go. Done.
I hope you can hear me.
Yes.
Thank you so much. But just as a note, you said we can write stuff in the chat. The chat is disabled, at least for me. The only thing I can type on is the Q&A, and then the Q&A based on the last session is kind of odd. If I type a question and somebody answers, I can't reply to their answer, just as a heads up.
Okay, so let me check here. Panelists can chat with everyone. I'm just doing this right now. Attendees can chat with everyone. How about that? Now try. Give that a try. Is it Serene? Am I pronouncing your name correctly?
Yeah, it's correct. Thank you.
Awesome.
Yeah, now it works. Great. Thank you so much.
Excellent. No, thank you, actually, because we had no clue. So that's fantastic. That's very important in a tutorial to be able to communicate with us into the group. So that's fantastic. So please feel free to interrupt anytime, any way you want. You can put your hand up. You can just, if we're ignoring you, just blurt it out, just unmute and say something, or write it in the chat if you want to be more discreet. By all means, just write it into the chat. We would appreciate that. Okay, so that's great. So I think we have the ground rules set. Are there any questions before we proceed? Does anybody have anything, any burning kind of no? No? Okay, excellent. So I'll just introduce myself. I'm just going to kind of introduce the topic a little bit. Ernest is he's the guy. He's going to be the hands-on guy for this tutorial. And I'm just going to give a little perspective from my experience in the field. And so I'm at the University of Toronto. My primary appointment is in medical imaging, hence my background. I'm in also in the Department of Statistical Sciences, which makes sense because I'm a statistician. I'm also in the Institute for Medical Sciences because that's where I apply my research, which is AI in medicine is what I do. Just to be mindful of my affiliates. So I'm a faculty affiliate for the Schwartz-Reitzman Institute for Technology and Society. So that is the application of technology in society. It's a research think tank at U of T. I'm a faculty fellow for community engaged learning. So if you guys don't know what that is, it's bringing together education and research, partnering with communities. And then last two, just for fun, I'm also affiliated with the Toronto Metropolitan University, which is another university here in Toronto, and with the University of Costa Rica, where I do my global health research. And actually, I'm going to be in Costa Rica in a couple of weeks. So I'm looking forward to that. So that's me. Let me just move forward. Okay, so what are we talking about today? We have a lovely title, essentially, but what we're essentially going to talk to you about today is trustworthy AI in medical imaging, or basically in machine learning, actually. I mean, obviously this conference is for medical imaging, but it applies for all of your machine learning, okay? So the biggest problem in statistics, or the use of statistics, is to deal with trust, right? How can we trust that what you're saying is true? So the first thing I want to say, just to put everyone at ease, and we have now 22 of you, which is a fantastic group, is you're never going to be wrong. Okay, so that's the first thing I want to say to you guys. If you come to my class or you work with me in statistics, you're never wrong. So that's something that I find is actually difficult and negative, that, you know, when you come and see a statistician and they tell you you've done the wrong test. Well, I'm gonna make you happy today, and I'm gonna say, actually, you're never wrong. Okay, and the reason is I don't know the truth either. None of us do. We don't know the truth. And that's the allegory of the cave. You can look up that story, you know, the Greek, you know, Socrates, described the allegory of the cave, but essentially we don't know the truth. And so statistics, the purpose of statistics is to estimate the truth. That's what you're doing. You're estimating the truth. So if you, and we're going to talk about it today. We're going to say, these are the tests that we recommend you do. So for instance, we're going to say you should do a paired t-test as opposed to an independent sample t-test, correct? So if you do an independent sample t-test, you're not wrong. It's not wrong. You're not bad. What it is you end up with an estimate that is further from the truth. So it doesn't mean it's wrong. It just means that your estimate could be better. So it's just a positive way of looking at statistics. So if we do a paired t-test design, we get a better estimate of what we want to do. Okay? So just to put you at ease, you're not wrong in statistics. It's just that you have to make the correct choice, right? In terms of, not the correct choice, the better choice in order to estimate what you're working with. Okay, so I just wanted to share that with you guys because that's something I know people have a hard time with, because when they go see statisticians, they're always told they're wrong, and it's very negative, and they don't want to go see statisticians anymore, and it makes my job very lonely. So don't worry about it, okay? Especially in this tutorial. Okay, so what are we going to be talking about today? So what I'd like to impress upon you is the reason that you'd want to do statistics, and I think this is the core problem, is that you make a claim of 95% accuracy with your model, which is fantastic. And then when you apply it in practice, it fails depending on where the new situation is, right? So that 95% accuracy is not representative. It's not doing your model justice. And I think that's what we want to address today. And so why? Well, there are many reasons, but certainly, the more key or obvious one is overestimation, right? So once again, we're estimating something, right? You overestimate it, so it's actually not 95%. You can also have what's called a spectrum bias. We would probably go through a lot of biases, right? That's something that you want to minimize in statistics. That's the goal of statistics, is to identify and minimize biases. If you'll remember from your stats courses, biases is a form of error, right? So there's two kind of big types of error, right? There's random error, and then there's systematic error, and a bias is a systematic error. It's a shift of your mean due to something, okay? So in this case, a spectrum bias is that your model was trained on easy cases, and that tends to be, can be a problem. You can also have the opposite, where you only test on extremely difficult cases, you know. Lack of robustness, so the model learned is having to deal with artifacts. And so that's something we can talk about as well. And then lack of calibration. So meaning that, does your algorithm operate across your range of data equally well across the range of your data? So, you want to be interpolation, right? Not extrapolation, interpolation. And so that is what calibration is. And that often, I'm going to say, like in our experience, I'm sure with Ernest as well, is that that gets missed. It really does, because you get very excited. You train your model, and you've done all the best way to get your diagnostic accuracy. Your measures of performance and everything is fantastic, and but then you don't take the time to actually test it to see how it's calibrated for your data, and that often is a missed step, which we're going to bring to light today. And it's just something you should keep in mind if you actually put this out in the real world, okay? Because that's when it's the most important. We're going to talk about pipelines, and we're going to talk about what's important in pipelines, and we'll ask you actually how deep a dive you want to go into this. But essentially, you have to keep in mind that from a statistical standpoint, so meaning that if you want to, impart confidence about your work, then it needs to go from the beginning to the end. And I think you'll be surprised that the beginning and the end for everyone is different. Like if you ask them, what's the beginning and the end of your pipeline, you're going to get different answers. And I think that's something that we can discuss today. But you can see here from my slide that the first point is design. So believe it or not, your pipeline starts at your design, okay? And if you look at the last point on this slide, you'll see it's reporting, and actually reporting is the last step of your pipeline. So if you think that, design and reporting was not part of your pipeline, think again if you want to be imparting confidence. And the reason for that is because in your design and in your reporting, you can actually introduce bias. And that is part of, basically talking about or reporting your confidence in your model, okay? Because how you report something can impart some bias, and how you design, how you chose the design of your approach could actually introduce bias, which would then reduce the confidence of your model, okay? The obvious ones, which, I'm sure you are all very good at, and that is, data handling, right? How we do it, how we prep it, the pre, the post, all that fun stuff. And then the model itself. So I would suspect most of you are actually really good at that, right? You've done it a lot, and you've come to this tutorial just to learn a little bit more about it, but you're probably all very good at it already. So the piece that we're going to try and add for you is a little bit more of a complete pipeline in terms of what we're expecting will help you in supporting the confidence of your models. Okay. So first concept for today. Do you have any questions, by the way, guys? If also, by the way, feel free to disagree at any time. You can fact check me as I'm talking. Please do. Give us a hard time. That's what a tutorial's for. Okay. Don't feel bad about disagreeing. Go right ahead. So the first concept is going to be proper validation, right? So these are concepts that are taught in epidemiology. But internal and external validation. So internal validation is within your study. External validation is when you're trying to look at generalizability outside of your study, right? So nothing new there for you guys. But the correct validation is going to help you. And we're going to talk about that today. We're going to get you to go through it. Ernest is going to walk us through that. But the reason I bring it up is just for you conceptually to remember that there's always two areas. So you need to report and justify internal validation, right? And you need to report and justify an external validation, right? So that's why it's always, or actually here, right on the slide, it says geographic validation is the gold standard. So meaning you want to go outside of your area, you want to go to a completely different data set from a completely different area, and or as an external validation to actually be able to appreciate if your model is generalizable. Okay. Don't forget, there's also, well, don't forget, this happens quite a bit where temporal, time as a dimension should be taken into account because data changes over time. So even though you think, maybe completely the same data over the last 10 years, it very often is not. And so there's another, opportunity for you guys to start digging in a little bit to the generalizability of your model is to actually think about that. Hey, I wonder if, the dimension of time has an effect on what I'm doing. Maybe not, but always good to think about it. Okay. Okay. Second concept. This one, I hope we're all experts. Okay. This one's, as a reviewer, when I review papers, it's a kind of, I got to do it. Like everybody's got to do it. And that's to look for data leakage because I'm going to guess it's probably one of the biggest problems I come across as a reviewer for sure. I suspect Ernest, the same thing. Data leakage is a big problem. It's a big problem. And the reason for it is not because we don't think of it. It's because we don't appreciate how the leakage can happen, right? So that's the key. And when you're really, a very talented coder like Ernest, for instance, then, chances are you're going to catch it pretty quick. But if you're a little new to the area, then you may miss it. And so this is the one time, I would say phone a friend. like ask somebody to give you a little bit of a hand, go through your code, and just, or your approach and help you in looking to see where maybe you have some data leakage. The obvious sign is when, you train your model and it's just amazing. Like this happens to me like regularly with my students. Okay. So students will come back to me. I know the data extremely well because it's my area of expertise. And they come back and they say, wow, I just trained the model and I'm at 94% accuracy. And I'm like, I don't want to burst your bubble, but that's not possible. It's just not possible because I know the area. It's not possible. And so then they go, no, I'm sure I checked it. And then no surprise when we actually dig a little deeper, oops, there we go, a little leakage. Okay. So we're not, I'm sure Ernest is going to pick up on it, but this is just as a concept, don't forget it. And as I said, phone a friend. It's always nice to have, a second pair of eyes on your data.
Can I add one thing?
Please, of course.
To the data leakage slide. Yeah. So I had a discussion with someone who is a top expert in the area of LLMs. And with the hot competition between companies and research groups to publish an LLM which is even better than previous ones, there's been many different tools and contests developed, like LM Arena, for example, is one of the most important ones. And she told me that nowadays training on test is one of the most important issues. And due to this competition, everybody wants to somehow access the data, and then the benchmark data sets quickly become obsolete, and the LLMs you see have already been trained on the data which is supposed to be used for testing them. So this is very important at different scales. For us in this tutorial, we are mainly focusing on local data sets, limited size data sets, all those things. However, be aware that this can be applied to different scales. Back to you, Dr.
Yep. Sorry, yeah. my unmute button disappeared off my screen again. Yeah, excellent point. And actually we're going to touch on that as well in the tutorial where things are progressing so quickly and becoming so big that we're encountering new problems, new challenges. And it's funny, you know, in terms of the theory, they're not new. It's always been there. But we're actually bumping up against them now because of our success. It's wonderful problems to have because it means we're successful. But yes, absolutely. Yeah, great point, Ernest, for sure. For sure, for sure. Okay, so we're on the leakage, learning curves. So there's some stuff I'd like to once again, like I started off on this presentation to say, hey, don't worry about it. You know, there's no wrong here. We're also going to share with you that some things haven't changed in many years. You know, and you think, wow, there must be a better way to do this. And no. So learning curves is one of them. Hasn't changed. Okay, so you know, trying for you to appreciate, you know, do I have enough data? Learning curves is still really, really, really the best approach. Either that or you've done it before. So for instance, in my case, you know, if I've done a lot of research in certain areas, I have a very good grasp at how much data I need in order, you know, to be able to train successfully because I've done it. You know, it's empirical. And that's very important, right? Learning curves is key. So just training with increasing sample size and just seeing, you know, what the curve looks like is really going to be very helpful for you. If you're hoping there's an equation, you know, like in stats, right? You have an equation, you have equations that can estimate for you, you know, the sample size you need for a successful t-test, for instance, right? Easy peasy, like really easy peasy, right? Unfortunately, in machine learning, it's not possible. And you're going to say, well, why not? Like, well, think of it, right? Think of how many parameters there are to keep in mind and that all the various possible interactions that you would have in a linear or non-linear relationship. It's just really that difficult to be able to, you know, calculate, estimate a sample size before you even get started. It's just really not feasible because it's too complex, okay? Can you do simulation? Yes, absolutely. But once again, very, very complex in order to simulate, right? So, you know, and I'd love to have the discussion. I hope someone tells me I'm wrong. I really do. I hope someone says, no, wait a minute, I know what it is. And you share it with us because that would make me very happy. So please do. But it's tricky and it, you know, to my knowledge, it's just not currently possible. Okay. Okay, the bias variance trade-off. So this is one where I think we need your help a little bit. And that is we can go down a rabbit hole on this one. I'm just going to keep it high level just so that we kind of understand where we are for this tutorial. But it's a tricky one, okay? And it's all to do with error, right? As you can see here, your total error is for in this case for the bias variance trade-off, your bias squared variance and your what's called irreducible error. And I'll show you what I mean by irreducible error if you have not heard that term before. This is a very simplistic representation of the bias variance trade-off. On the left are the classic, you know, kind of accuracy, right? So just showing low variance and low bias, but you use this for precision when you're talking about precision, the same idea, right? Because it's the bullseye. And on the right is the graph, the classic graph that shows with increasing complexity of a model, the change in error. Okay. And what we're looking for is basically the sweet spot, right? So we don't want an underfitted model, which is in you know, what would it represent? Would represent a biased model, right? Or an overfitted model, which would represent a high variance model. So don't forget, it's comparing models here. When you say high variance, it's not high variance in one model. It just means that from multiple models, when you're using different data sets, you get very, you know, basically overtrained, right? So meaning that each model is very specific to that data set that is being trained on from that population, let's say. And so then inevitably, because it's trained specifically to that data set, it's going to differ. And so then you have what's called high variance. So that's high variance in your models. And that's the high variance on the right side of the graph, right? And on the left side is bias, where it's just extremely crude, right? It's very simplistic. That's what happens with a high bias model. For instance, if you were to estimate the height, let's say we wanted to know the height of the next person that comes to our tutorial, right? So the easiest way for us to estimate that we would just ask everybody for their height. We'd take the average, and then we'd say that the next person that's going to join the room is going to be the average height. Pretty easy, right? So that would be extremely biased, wouldn't it? It would be a biased answer, right? And the reason for that is because we're not taking into account a whole bunch of other things. Like the most obvious would be sex, for instance, right? So on average, men tend to be taller than women. Not always. There's an overlap, of course, but so then we added one parameter. So the more parameters we add, the more we improve our model, and we approach what in the middle of the right figure is the sweet spot. So meaning that we're not over parameterizing, but we've put in enough that we get a good answer. So that's the blue area, the optimal zone. Okay. And that's where variance is increasing because we're including more and more parameters. And therefore, if there's more and more parameters, the algorithm can train those and weight those parameters to make better decisions, right? But if you do too much, if you have too many parameters, and you have too much memory, essentially, then you're going too far, right? We're also reducing the bias, right? Because we're adding some complexity so we can make it better. So the question that you should be asking, if you haven't seen this before, is for the total error, why the heck don't we get down to the bottom? Why can't we reduce error to the bottom? Right? It's a good question. Well, that's the irreducible error. There is always a component of noise or error that cannot be reduced. No matter what you do, it will always inherently exist in your data set, and that's okay. That's part of your data. Is it always the same level? No, it depends on your data, okay? That's irreducible error. So that's the concept of the bias variance trade-off, that you want to be able to find that sweet spot so that it's generalizable, because it's not generalizable if you overfit a model. So if you have very little data and a lot of parameters, it gives the model the shortcut, right? The ability to memorize the data for that data set. And so that's the the overfitted model that you want to avoid. But then you want success, right? Because if you use, just as I explained, the mean, right? If you just use the mean for height, right, to predict height of someone coming in the room, that's not going to work well for you, right? You know that accuracy is going to be, right? It's not going to be good. And so that's the reason that you're looking for the sweet spot. Okay. So that's, in a nutshell, there's the bias variance trade-off concept, which is very important, and you should all be very comfortable with that concept in order for you to understand how to validate your model, how to generalize your model, and how to work with your model, right? So now that I've said all this and it's all wonderful, now I'm going to take you to something that it has not been proven yet, but is being talked about a lot these days, and that's called the double descent. So if you haven't seen this before, it's because it's not like 100%, but it's an interesting concept, right? So the interesting concept is, if you look at the same figure with model complexity and your error, you'll see here, or you'll see, and I don't, do I have a pointer? I don't know if I have a pointer. I should have a pointer, right? Here it is. Laser pointer. Haha! Look at that. Fantastic. Okay. So you see here on the left, this looks very familiar, doesn't it? Right? That's your test error. And you remember that from the previous slide, that you have your sweet spot right here with your irreducible error right there. Perfect. Okay. And as your model complexity increases, your test error goes up. Oops, I've gone too far. Correct? Clear. If you look at your training error, you've got your training down to 0. And that's when you get down to 0 for the training error. It's what you call your interpolation threshold. You've hit the max, okay? So here's the theory. If you keep pushing model complexity into what's called over-parameterized models, you actually start to see a descent again in your testing error. And so in theory, some people still don't believe in this, but empirically it's happening. And this is what's happening with your GPTs. So the extremely large, clearly over-parameterized models with a ton of data, we're actually improving again. Because it wouldn't have made sense, right? It wouldn't have made sense. We're starting to include billions of parameters. What? So that means that this should be just continuing up here, right? We should just like continue here, right? It should just be getting like worse and worse and worse and worse and worse, but it doesn't. So anyway, that is the double descent. Feel free to disagree, agree. It's out there. Google it, check it, do whatever, whatever. But just keep it in mind. It is interesting. It is interesting. And it has kind of partially explained the success of these massive, massive models. Right. Anyway, there you go. So there's a concept for you guys to mull over and think about. Now we're going to get to this calibration situation here, right? So what am I talking about when I talk about calibration? And as I said, we're going to go over this with an example. But the bottom line is when you're calibrating, what you're looking for is whether or not its ability to predict is consistent across your data range. Okay, so it's nothing super special. It's been around forever, and it's called the Hosmer-Lemon test. If you've ever worked in logistic regression and stuff like that, and it's something that you should perform if you're thinking about putting this out into the real world. And so essentially you're grouping your subjects, participants, whatever you're predicting, right? Let's say people in our case, or doing medical imaging, right? On similar predicted, probability values, right? So you just rank them, right? And then you group them into, let's say, deciles. That's usually the more common what everybody does, right? Essentially is they put them into deciles. And then you compare the number in each decile of predicted and reality, right? And you want to see if that number is consistent across your 10 deciles. That's essentially where you're doing calibration. Okay, that's in a nutshell, that's what we're doing, and we'll show you later on. But that's what we're doing. And you're going to say, well, why are we doing that? Well, it kind of makes sense, right? It kind of makes sense. We want to see that our ability to predict is consistent across our range, right? Our full range of data. That's what it's saying. We don't have these areas that are better than others for our model. You could argue, well, I'm okay with that. Okay, fine. But you would need to report that, right? So instead of saying I have a nice fully calibrated model, you would say, well, you know what? Our model has some weaknesses in this area of the data or whatever. Maybe as a statistician, I wouldn't recommend it, but if you're stuck and you have to, maybe. But this is a good way of just knowing, should I move forward? Should I not? How am I doing? And so looking at this figure that I've showed you, I'd be pretty happy with this. I don't know about Ernest. I don't know, maybe Ernest is pickier, but I'm like, I don't know, that looks pretty good, right? But if you have some points that are out here, like just way out, or if you have this kind of weirdness, where near the end or whatever, that's when you would need to worry. And in that case, you would need to retrain. Essentially, you've got to work with your model. You got to rework your model. Okay, that's the theory. And think about it. Ask us some questions when we get some hands-on. Okay. This one, I'm going to keep this really simple. And that is like, actually, what, do me a favor. Everybody here's in the group, we got like 24 participants. That's wonderful. Put your hand up or give me a thumbs up if you are clinical. Like, are you hands-on clinical? So you guys are working in, or supporting clinical work, kind of more hands-on, or are you kind of back end like engineer, or, this is all, you're all in the informatics and stuff like that. But if you're clinical, I don't even know how I'd be able to see that. Maybe Ernest will see it. But anyway, put your hand up or something. Let's just see if the thumbs up or hands up can work for you guys. Oh, we got a few. Okay, excellent. So that's great. So the concern here is the same as when I talked about it earlier about ClinEpi. Is it useful? What? Right. So this is something to think about, and that's my area. So my area of research is utility. So actually getting algorithms to work. I don't really care how complex they are. I don't care how cutting edge they are. More important for me is their impact, right? Are they actually doing what they're supposed to do in practice? So for instance, as a term, if you've ever been in the world of drug development, and that is the difference between efficacy and efficiency. Okay, so I don't know if you've heard that, but efficacy means, does the drug do what it's supposed to do, right? But efficiency means, is it working in the system that you're developing? So that would be the person, right? So if you test in a randomized controlled trial, that's efficacy, right? It's controlled. Some people get the medication, some people don't. They're told when to take it, how to take it, and they were recruited into the study. Efficiency is going to be that person who, I forgot to take it today, or, oh, I'm supposed to take it at night, but I like to take it in the morning. Or, if I'm partying this weekend and I know I can't take this drug when I'm drinking, but you know what? It's a Jays game tonight, so I'm going to be having a couple of beers. I'm not going to. So that's efficiency. So that means, does the drug work in the real world, in the system? So when you're developing algorithms, it's the same idea, right? So what you want to do is you want to make sure that whatever you're developing is actually doing what it's supposed to do. And we're going to talk about that later on today. And that is when we talk about agreement, versus reliability. So agreement means that the measures are precise, they're the same when you repeat it or whatever. But reliability means, am I able to, discriminate between patients, so disease, no disease, or something like that, and make a decision. So decision making. So there's the difference. So when you're doing your training and you're thinking, I want this to be accurate, right? I want this to work well and with my performance measures. Always think of the next step after that, which is it going to permit the actual decision that I want it to? That's the next step. So that's clinical utility, okay? So not only the statistics and the precision and the accuracy and all that fun stuff that just gives you this, but think of it at the next level is the way it's going to be used. Is it actually going to be useful, to clinicians, let's say, or to make decisions for decision making? And in that will come, of course, confidence. So then you're thinking, well, whatever, that's not my problem. Well, actually, it is your problem. That's what you need to report and provide the people who are going to use your work. You have to provide them with that confidence of, can I actually use it, right? How confident can I be with my algorithm? That's statistics, okay? Wonderful. And that leads really well into the reporting and reproducibility. And that is, how do you report it? So I just put tripod start claim. There's a whole bunch of checklists out there. And that's not the purpose of our tutorial. All we're just trying to say is, hey, pick something, a standard way of reporting that is in your discipline, in your area of interest, where you're publishing or who you're working with, and stick to it, okay? Make sure that you follow these standards, these guidelines. They're there for a reason, and it's to provide everyone a way of understanding what you did to enhance trustworthiness, right? The trust in what you're doing. That's the reason we use them, okay? It's not to make it onerous and difficult for you. It's really just so that you get this trust, right? That what you've done is appropriate. All right, so that was the end of the pipeline. Okay, so now, Ernest, I think I just have this last paper just to give as an example of what we just said, and then we're good, right? Then we're going to launch. Is that about right? Yeah. So I'm just sharing. This is outdated. It's outdated, but I'm sharing it because I like it. Like I use it all the time. I teach with it. I like it. So it's in radiology. No surprise. I'm in medical imaging. I'm in radiology, but it was in a paper from 2021, I believe. Yeah, European Radiology. And it's how to review papers on machine learning. So is it dated? Yeah, it's dated. So be careful about that. But what's really nice are these figures. I just love them. They put these figures, they're fantastic, right? And so these figures just show you, for instance, here, your full pipeline. All right, so everything we just talked about. essentially from design, data handling, modeling, and reporting. It just gives you a nice idea. And then the test set, locking away your test set, right? And we're going to talk about that, shortly. And then it gives you the concepts about your the steps that you would take in your study, which of course we just went through the pipeline, design, data handling, modeling, and reporting. But then it breaks it down to, hey, pay attention to this. So you'll see in data handling, the first one is information leakage, right? And then the feature scaling, and Ernest could give like a full tutorial on every single one of these boxes, right? There's just so much to talk about. But this just gives you a nice summary so that you don't forget. And the ones that are often forgotten, as I said, is the beginning, design, right? And then reporting that I'm just stressing for you guys, because data handling and modeling, you guys are probably all pros, so you're all good. But this is just a reminder, okay, to check all of these off when you're doing your project. All right. This one here is the splits. So this is where, and I'm just going to touch on it really, really quickly, and then we're going to actually do it hands-on. All right. So this one is, what do we do? So everybody, like, I don't know how long all of you have been in medical imaging, in machine learning, but this whole split thing, the first, like, I don't know, when did I get started? Like actually working on AI or machine learning programming was, I don't know, 7 years ago now or something like that, right? So at that time, it was a single split. Like, it was a single split. Everybody you know what we used to argue about or like worry about is, are we going to do 70, 20, 10? Or are we going to do, 80, 10 and 15 and 10, like it was like, how do we do our split? And which is a bit silly, right? Because it's really not a big deal. But anyway, that's what the talk was back then, right? Single split. But then we realized, wait a minute. Depending on that split, because of the wonderfulness of randomness. So I never complain about randomness, and you shouldn't either, by the way, especially if you're in my world of statistics. If it wasn't for randomness, I'd be out of a job. Be kind of boring. So you got to enjoy randomness. But one of the downsides of it is, where's that split happening? And maybe it was a bad split. Oops. Right. So that's where the concept of cross-fold validation came out. And so if you look in here on the graph, you have the classic cross-fold validation. All right. And did that improve things? Yes, it certainly did. Along, what comes with it is some complications, some challenges, and we're going to talk about that. I mean, how do you report it? How do you make statistical differences between mean accuracy, accuracy or mean accuracy for folds across different models? So we'll talk about that. But there's another one, which is, I think, and correct me if I'm wrong, not as popular, which is the random splits, and lots of them. So you just randomly, right, to do this many times. It's just computationally heavy. I'm not saying it's bad. No, it's not. I think it's great. But I don't think it's as popular just because it's very computationally heavy. Okay. And then the last one, which I think is probably the go-to these days, is a nested crossfold. And so that one, the difference is you introduce a test as well. So you do have the 3 splits, and that permits you, which is a little bit annoying maybe, I don't know. Each one, you're tweaking the hyperparameters. So that gives you more work, but it's kind of cool, right? In that sense. So we can discuss that. Actually, I'd love to have a discussion on that one, because the crossfold, it's you're just moving the blocks around, but your models stays the same, and the the hyperparameters and all that, it's all the same, right? And you're just moving it around, and then you get your accuracy for the different blocks, right? But in this one here with your test set, it permits you to tweak the hyperparameters within the training validation and then test for each one of these folds, right? It's kind of a cool concept. And so I'm going to throw it out there, probably gold standard these days is the nested, if you can do it. Like, it is computationally heavy as well, and it takes more time, but it's not bad. And then the last thing I'm going to say on this one, which is not on this, is don't forget, if you're going to push this out the door, and sell it, let's say commercialize it, which one do you use? Right? Tricky one, right? Because you can split off a test set at the very beginning. You can have a model here. You can have a model here, and you have multiple models here. So which model do you actually push out the door? So we can talk about that. Typically, if you're going to commercialize, you do another model on all the data. No test set, no nothing. That's the model you push out, right? So you literally just take all the data, train it to the best of its ability. No test set, because what you're going to report as accuracy is going to come from these. But the model you're actually going to use would be the one with the most data. I guess if you have tons of data, then you don't have to worry about it. If you've saturated, but if you are a little bit limited for data, then you're going to want to test on all the data. Anyway, we could absolutely talk about this. You tell me what you guys do. That would be an interesting discussion.
We have one question. Kim, can you please explain how do we choose the hyperparameters in D, which is nested cross-validation?
So the nested cross-validation, so you're saying because you always, every time you get a new data set, you want to improve your model as best as possible for that training, correct? Like that's, every time you start with a data set, right? You have a training and validation, and you run it, and you're permitted. You're allowed, right? That because you're training and validating, you're changing the hyperparameters in order to get the best model for your training and validation, correct? And then you test, right? That's the process. So in this case, you're permitted to do that for each fold in a nested that because you have a training and validation and a test set to provide you with the test on it. Does that kind of answer your question? Make sense? Ernest, is there a better way to answer that?
I think you nailed it. I would add a couple of different things. There is a slight difference between nested CV and also a nested K-fold CV. So there are the technical details are a bit different, but it's not hard to imagine. Let's say you have nested K-fold and K is 5. So you split your data into 5 partitions, and then for validation or hyperparameter tuning, you have 4 remaining folds. Now, one way is that you can iterate over these 4 folds and test different hyperparameter settings. Now you can exhaust all your settings, meaning that in each of those 4, you test every single combination of your hyperparameters and you come up with the best one, and then take that and apply it to the outer loop, which is reserved for testing. So that's one way. The other way to save some computation resources is to just randomly pick some combinations and apply them to different inner loop folds. That's another way. If your data is bigger, if your models are heavier, if the computation is super duper expensive for you, you can also use this and it is valid. There are different ways. To put it in a nutshell, I would say whatever you do is okay. Just keep the test part unseen. That's it.
Excellent. Yeah. Excellent. And we can talk about that more. That's the purpose of this tutorial. So when we get to that stage, maybe Ernest can address that again. Does that answer your question? Yeah, for the actually I don't even where'd you get that question, Ernest? That's funny. I don't see it.
It came from Q&A, and we
Q&A.
don't have
Okay,
the
I'm not
name.
looking at that. I got the chat. Okay, excellent. Anyway, that's good. I'm just trying to keep track of what we're doing here. Excellent. So I'll move forward. If there's more, if you will have another question on it, we'll go over it. No problem. That's wonderful. Okay, and this is sample size and summation. That's for later. So actually, perfect segue. I think now we're moving into some of the hands-on, correct, Ernest?
I believe so.
Excellent. Well, I will hand it back over to you then.
Okay. Let me share my screen. And do you see it?
Yep.
Awesome. And move these things around. All right, so this is LM Arena. I mentioned during the point I had for training and test. It's nothing. I put the link to our GitHub repository in the chat. Please use it. We have all the data, all the codes, and also the presentation files there. These are the files you can use in your research, hopefully. I put everything on my Google Drive as well. Initially, I wanted to go over all the codes, cell by cell, run them, but then I thought if we save time on running them, we can cover more. So anyways, we have designed this tutorial to have three hands-on parts. Part one is for classification, part two for segmentation, and part three for regression. And the reason is that if you look at any ML pipeline or AI pipeline, there is input, there is model, and then there is output. The way you can apply statistics to make it robust and reproducible is either to apply it to the input or somewhere to the model or the output or a combination of them. And so here we are focusing on the type of output. There are other types of outputs that you may face during your career in medical imaging or medicine in general. For example, you may have survival analysis, but the main three categories are these. We wouldn't have time to cover every single pipeline. Classification, I would say, is perhaps the most important thing. So let's go to the classification, and the way I organize my projects, um, inspired by a book I read years ago from one of the grandmasters of Kaggle, is to create subdirectories. We have code, data, and sometimes we have also results. And nowadays we have more, but code and data are always there. So inside data, what I've used for this part is a radiomics dataset. If you don't know what radiomics is, it's my love. So radiomics means you have medical images, you create regions of interest, meaning that you just segment the image, you get, for example, the tumor out. And then there are tons of predefined formulas. Some are very simple, like just surface area or tumor volume. Some are very complicated, higher order features. And once you extract all of them and put them together, you get a sort of tabular data with multiple columns for different features. These are the columns I have here, so you can see that we have, for example, patient ID, subregion. These are just the features we don't use for classification. But if we go further, after diagnostic features, we get to shape and etc. So that's the concept of radiomics. Now we have this tabular data, and based on these features that we have, we want to conduct a classification. This example comes from the Open Radiomics dataset. We have high-grade versus low-grade gliomas or brain tumors. These details do not matter that much. What is important for you is to know that we have tabular data. It's a classification. It's a binary classification. We have some features, and we want to do that. Going to the codes, I've numbered the codes so you know which one comes first. We start with train test ratio, which is connected to what Dr. Pascal covered related to data sufficiency and dataset size, sensitivity analysis, etc. So of course, first you need to import the needed libraries. Let me zoom in. That's the import part. If you are on Google Colab, you run the cell just to mount your Google Drive and get access to the data. What you need to do is to provide a path which applies to your setting. This subdirectory is on my Google Drive. You can change it, and then we change the directory, and now the code works. If you run it locally, just forget about this cell and jump to the next one. To load the data set, all we need to do, now that the paths are set, is to use relative path. So we are in the code. So the data path will be double dot data and then the name of the CSV file. Pandas reads the file for us. It's not that much complicated, and we can take a look at the data frame. We have 369 rows and over 1,700 columns. The ground truth label, the column is named group label. It's a binary variable. And then to fork X, which is the predictive features for us, we need to drop some of those unneeded columns like lesion ID, group label, etc., etc. We do that. And then what we do is that for this specific case, we stick to area under the ROC curve. You can change this to any other metric that you want. And you can also enable multiple evaluation metrics, as you know, and report many of them. Now, what we do is that we iterate over possible test to train ratios from 90% to 10%. So what we are doing is that we do this classification based on different test and train ratios. For each ratio, for example, let's say we dedicate 10% of the data to training. We repeat this 100 times. All right, so that's the concept. And then we evaluate the model using AUC, and we capture AUCs so that later we can plot them and see what is going on. So that's the idea we have. Now, we just have a very simple loop. To keep things simple, we don't have hyperparameter tuning here, so there is no nested thing. It's just train test. It saves you some time if you run this, depending on your computer. If you run it on Google Colab, I think just for training these, you would need something like 20 minutes or so. So it's not that simple, and we just wanted to keep it quick. Anyways, you do this, and what we capture is the minimum AUCs, maximum AUCs, and then the average of them, so that we can come up with a plot like this. Maybe I have zoomed too much. So this is the result we get. Starting from 10% of the data being used for training the models, which is on the left, going all the way to using 90% of the data for training and using just 10% for testing. As you can see, at the beginning, the performance level is okay. It's because this classification seems to be simple. Even with, if you remember, we had 369 patients. So 10% stands for something like 37 patients. So with 37 cases, your model can learn to do this classification. However, the variance of the performance, as you can see, the range is quite broad. As you move on, for example, for 50%, 60%, that's the sweet spot for you. You get something bounded and the performance is quite high. As you move on, you get to higher average performance, although it's getting plateaued. However, again, because of small tests, you are facing some wide range of performance for your models. So you put this into a summary table, you save this, and that's the first part we wanted to cover. This ties back to what we talked about, dataset size sensitivity. And there is one paper from 2 or 3 years ago. We had a research on this topic. You will see similar plots. It was a different data set, of course. However, the concept was the same. So that's notebook number one. Dr. Tyrell, do you have any final comments on this, or should I move to the next one?
No, unless there's any questions. No, that was great. Unless anybody wants to ask, and it's a good time to ask. If I have all my windows open now, so chat and questions. Does anybody have anything they'd like to ask or any?
Since
No?
I cannot see the chat and the panel, please feel free to stop me.
Yeah, for sure. And I'm keeping an eye on it, and right now we're good. So there's no nobody
Okay.
asking. So,
Okay, awesome.
I think we're good. Yep.
Perfect. So part two is about data splitting. So we are using the same data set, same concept. So the beginning of the codes are exactly the same. We can skip all the way to the end of creating X and Y. And then we want to compare different cross-validation strategies. So what we have here is a repeated fourfold. So we repeat this again 100 times. So a repeated fourfold cross-validation, that's the first strategy. Second one, just a fourfold, so one time repeat, a fivefold, a tenfold, and the last one is just something that we call it Monte Carlo data splitting. So it's repeated random splitting. And then our ground truth will be one out, which means if you have 369 patients, you will have 369 experiments. In each experiment, you dedicate exactly one patient to test, and you use n-1 to train your models. And we want to compare these. I don't want to go over all the details here. Again, we are skipping the hyperparameter tuning. However, this is the most important thing we want to cover in this workshop. Not the whole workshop, but in this notebook. Anyway, so on the right, we have leave one out. So leave one out, the beauty of it is that you get one inference, one predicted probability, one predicted class label for each patient. And if you put them together and get the average, there is no variance. It's just one time. This enables you to do many different things. And during my PhD, a module of my thesis was dedicated to this. For example, let's say you want to report the performance for male versus female patients. With leave one out, it's super duper easy because you have exactly one inference for each patient. It's just a group variable. You separate the two groups and you report the performance for them. Whereas with other strategies, you need to be careful which one was used in test, which one was in validation, which one in training, and then taking into account all those variabilities, it makes your life a bit harder. However, as it was mentioned during the presentation, it's computationally expensive. So the next is repeated random splitting. 75-25 was what we used. As you can see, there is some variance. However, the mean performance is quite similar to what we have through leave one out. This is why I personally love this Monte Carlo data splitting, but I understand that, for example, if you're using deep learning models, it's not easy to repeat your experiments for 100 times. It's not even feasible in majority of the scenarios you face. So how about moving to a different number of folds, a k-fold cross-validation? Well, with 10-fold, the mean performance is a bit higher than leave one out. So if we consider leave one out to be the golden standard, which is in this scenario, in my opinion, maybe you have different experience, please feel free to share it with me. But in this scenario, it's the best you can get out of your data. And if you put that as ground truth, then 10-fold is a bit off, but not that much. And also the range, you can see it's a bit off. It's not representative compared with the repeated data splits. 5-folds, even worse in terms of range. 4-fold, again, 4 and 5, they're not that much different. You change your seed and you see different results. And repeated 4-fold, in terms of range, you get the best range, so it covers all those extreme cases for you. And the average is not bad. However, it's not perfect as Monte Carlo. And in my experience, based on multiple different projects, usually that's the case. I don't know why. Repeated 4-fold should be in any ways better than Monte Carlo, because for sure you know that all examples are exhausted for the experiments equally. However, if your data set is small, if you have outliers, I believe those are the drivers to push your results out. And finally, you get some summary statistics. So you get mean and standard deviation for different methods you have, and save it. So that's about data splitting. Again, I'm gonna go nonstop, but feel free to pause me and ask any questions you have. Next is gonna be calibration. Um, I don't know if there are any questions yet or not, but anyways.
Yeah, actually, you know what? Why don't we just pause for a second there? Yeah, go back to that one. I like that one. So let's tie this back to the you tell us actually, Ernest, based on your experience, the concerns with generalizability, the concerns with overfitting versus so high bias versus high variance models, right? So that's the whole bias variance trade-off. And then the last one will be personalized medicine, right? So how do you balance all that? Because everything you just talked about is fantastic, and it brings up all of that, right? So the leave one out versus your Monte Carlo versus your repeated 4-folds. What in your experience, how do you decide what to go with? Because I think if I was sitting in the audience, I'd say, okay, well, which one do I choose? Like what should I go for? What do I do? What do I do? So in your experience, what would you suggest?
That's an excellent question. And the answer, in my opinion, is that it depends on the situation.
That all answers in statistics.
Yeah,
It
of course.
depends.
Of course, I do. Let me share a story. I was working on a project, and you know what the project was, but I'm sharing that with everyone. Um, we had an interdisciplinary project. It was something between oncology, radiology, surgery, and then AI. I was working on it. At first, there was no prior literature on that, so whatever we published, it would be amazing. Even a single data split, 4-fold, 5-fold, it wouldn't matter. Because it was the first time, journals would love it, and that's actually what happened. So we used a 5-fold cross-validation using 120 patients, and it got it out. It was fantastic. as the project got mature and we added more patients to the data set and we published more, we dig more, we started to have more regular meetings and discussing the possible ways to push the boundaries a bit, do further research. And one day, one of the oncologists asked that, hey, Ernest, if I give you a patient ID, can you give me the predicted probability for that specific patient? I was like, well, I need to go back to my codes and see if the patient was assigned to training or validation or test or blah, blah. So then I learned a couple of things, and in the next publications, we completed the pipeline. First, and this is again one of the points from that book I mentioned, the machine learning book, to deal with any problem and to have a systematic approach to developing your codes. So the first is that always, 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 when you do data splitting, if it is k-fold or one-time data split, document it. Have a CSV file holding all those IDs. So that was the first learning. Second, I realized that with radiomics, my models were not that complicated, or I could use simpler models. When I switched to tree-based models and simplified the pipelines, then the computation load was not that high. Then I had the flexibility of using this leave one out setting. And then I could answer the questions very easily. When you have leave one out, give me your patient ID, then I give you the predicted probability. It's super duper easy. But if you're working with deep learning models and it takes several days or weeks to train your model, that's not feasible at all. So depending on the scenario, if you can leave one out is amazing. It depends on two factors. One, computational load, and that's relative. If you have a 5090 computational load is defined differently for you than when you have a 3070, for example. So that plus dataset size. If you have 10,000 patients, then leave one out is gonna be a nightmare, even if you're working with tree-based models. So those two factors, and then k-fold. If you can repeat it, or if you can go for 10 folds at least, and we will see why in module 5 of this classification course, we will see why. If you can increase k to 10, that's amazing. If not, do your best.
Awesome. Yeah, it's always a tough one answering that, and that's great. I mean, that's based on your experience, that's fantastic. The only thing I'd say is I think the leave one out is definitely a holy grail, like in the sense that if you want to progress towards personalized medicine or precision medicine, then it's great, right? It's very useful. If you're looking for the best model, maybe not, right? Because it definitely, when we were talking about bias variance trade-off, you're definitely going to get low bias. There's no doubt. Like, with the leave one out is fantastic. You're using the most data, right? You're using all your data to train, except for one. So that's fantastic. But then because you're only testing on one, then you kind of introduce higher variance, right? In that sense, because each model is going to be specific. So there, it's going to be a little more volatile, right? Like in terms of your results. So I think you answered it perfectly. It really does depend. Like it really does depend. So do your research, in terms of that, how to get through that. So let me just see.
Yeah, we got one question.
There's a question. There's a question. So I was wondering, Professor Nemdar mentioned a few times a book with guidance on machine learning. To which one is he referring to? So Ernest, if you could just, when you have a moment, put the reference to your book in the chat or something like that.
Exactly. Sure.
Nina was asking, but
Sure.
we're happy to do that, Nina, of course. Oh, we have a question. Serene, please.
Yeah,
Please
thank
go
you so
nuts.
much. Just to reiterate, like a past comment that you mentioned in the presentation. So you said if we want to put the model out there, sell it, put it in a hospital for them to work with, we just retrain the model on the full data. And the cross-validation and everything we're discussing now is basically to choose which model or which hyperparameter to put out there. Am I correct?
Well, it's to choose and to report your
Yeah, to
accuracy,
choose and
performance
report
accuracy. Yes.
the
Yeah, that's correct.
performance.
I mean, if, as I said, if you have enough data, like that's going to be like almost a corporate question, right? So in terms of when you want to put it out and you want to validate it, but if you have sufficient data, you know, like there's ridiculous amounts of data that you don't have to worry about, then you can certainly keep a test set, you know. But there's not really any point because that's what you're doing the cross, you know, do nested cross-fold, you can do leave one out, you can do all of that, and then that's going to give you your performance metrics, right? That you are going to report and say, this is what I found, right? But the model you're actually going to deploy and put out there and sell it and, you know, and use it would be most probably is on all the data, right? Because you're trying to do as much, you know, trying to get the best model for all of the data you have, right?
Yeah.
Ernest, please jump in if you have, you know, if you have different ways. But that's pretty much the industry norm. But you know, it really depends on who you are and who you're working with, for sure. And then also, and Ernest, I know you're itching to get in here. The other thing you must do, right, is you're going to do a silent study anyway, right? So a silent study is going to be, you're going to have that model and then you're going to test it prospectively with or directly compared to your gold standard, right? So if you're trying to, let's say, diagnose something, then your algorithm is going to do the detection, binary classifier, yes, no, disease, yes, no, cancer, yes, no. And then you're going to have the experts who are going to be doing their job. Let's say a radiologist, they'll be doing their job to detect the cancer at the same time. And you do a head-to-head comparison. And that is called a silent study, prospective silent study. And those are required in order for you to get through regulatory compliance. So for instance, I don't know if you're in the United States, I'm going to assume we are because we're in Atlanta, that would be the FDA.
I
Okay.
would like to add a couple of notes.
Please.
So from technical perspective, there are a couple of different scenarios that will lead you to do different things in this regard. Let's say you're training a massive data set. So you're doing machine learning at scale and you're training, for example, GPT. If that's the case, then absolutely. You put everything for training because it is at scale. It's a different paradigm. And you train it until it learns all the data. And then you have something which is called a large language model. So it is a model for the whole language that you have. Now, switch the lens and come back to working with limited size data sets. Now you have MRI scans from a couple of hundreds of patients. So it's not that big. It's not a large data set, and your performance is not expected to be that high. You do all these things, and now you want to sell it. Well, there is another concern, and this time it is regarded to your design. Let's say you're training a deep learning model. When do you stop your training? This is limited size data set, but this is going to be a startup, or you want to put this into production at a hospital. Uh, well, if you run your training for 1 million epochs, or there's no constraint for stopping, then you don't know where you will land on that curve that we saw, underfitting, overfitting, or the optimal state. So still, you need to have some sort of validation. However, before you had train, validation, and test, and now to get one model for production, it is one-time data splitting, and it is just train and validation. Or you have another way, which means you have k-fold, let's say four-fold cross-validation. So 4 times just train and validation, and then what you put out is an ensemble model based on the 4 models you train from each fold. That's one scenario. Now, what if your algorithm is not deep learning and you don't have the concern for when to stop the training? What if you're fitting a random forest or XGBoost, whatever? Well, XGBoost is a bit different, but random forest is a perfect example. And actually, in one of my papers, I highlighted that. You do this train validation test. Based on validation performance, you choose your best hyperparameters. Okay, bingo, you got your best set. How should you test? Based on my experience, it was always better to combine train and validation and train another random forest example based on your best setting, and then go for test. So if that's the case, then again, you can combine everything. So it is limited data set size. However, you don't have train validation test. It's just training. Training and using the best hyperparameters, just overfitting one random forest to the whole data set.
So once again, it depends. I love it. It is. I mean, we're joking, but it is absolutely the truth. That's an excellent question, and I get, you know what? Why not? Let's have some fun here. Let's make it worse, and actually, I'm going to make it worse, and I'm going to make it easier for you. Okay. So from an FDA perspective, or from a Health Canada, depending on where you are, you have to lock it down. That's the rule. You have to lock it down. So you have to choose your algorithm and lock it down, right? Here's the tricky bit. For true generalizability, you're going to need to retrain anyway. So I'll give you a very short little snippet. I'm working with the government in Costa Rica in order to implement AI into the healthcare system there. So as you can imagine, most algorithms today come from North America, most often. And they're trained on data sets that are either North America or China. Those are the largest data sets that are available today. It's changing, but that's basically it. So you can imagine implementing an algorithm that's been trained here, no matter how we did the testing, the splitting, and no matter what, we need to retrain it anyway when we get to Costa Rica because the population is different. So our ability to actually, implement an algorithm straight away out, from our box, out of the box, is going to be limited because it's not generalizable. It's not fully generalizable because it wasn't trained on the population in Costa Rica. So there's another little caveat for you. No matter how you slice it, dice it, switch it, test it, whatever, and lock it, just remember generalizability is going to be a challenge for you if you're not just working with the data that you trained on. Like seriously, that's basically it. The data you trained on, that's what you're working with. You can do lots of fun things, but the reality of generalizability is a different thing. And just be prepared for that you are going to need to consider basically retrain when you get to a new jurisdiction or a new population or a new culture or whatever for your work. So be ready for that. Don't think any algorithms should be locked down forever. They can be, but just remember, and that's what we're covering in this course, right? Is that's the challenge, is if you lock it down, it's going to introduce error essentially, and then you're going to have to either embrace that error and live with that, or you're going to have to retrain and try and improve your model. And I think moving forward, that's the new way. We're going to have a flexible enough environment to provide the ability to retrain your models regularly, right? And that's something that's being considered right now in terms of how we govern AI, is that ability to do exactly that, right? Because we don't want to make it too onerous for you. Let's say you have a startup and you have this wonderful product. We don't want to make it too onerous for you to be able to do that, to retrain it and improve it without having to go through full regulatory on every occasion. Anyway, there you go. Another fun perspective. It's 3:30. We're halfway. Are we not, Ernest?
We're halfway done, and we can take a break if everybody.
Yeah. What does everybody want to do? Would you guys put it in the chat or put it in the chat if you don't mind. Would you like to take a little bio break, like even 5 minutes, just to walk around, stretch a little bit, go have a drink, go would you guys, is that okay? What do you guys think? You guys out there? Yeah. Well, right now it's kind of quiet on the answers. What do you guys think? Anybody throw it in there? Let's take a minute. Okay, Rosa made it. That's it.
Okay.
Serene and Rosa made the decision for the whole course. That's wonderful. Yes. Okay, so is 5 minutes good? Let's take a 5 minute break. What do you think, Ernest?
Yeah,
5 minutes?
sure,
Yeah.
sure. Awesome. Yeah.
Okay, let's do 5 minutes. Let's come back at 3. We'll give 7 minutes. 3:35. How about that? Fair?
Yeah, okay.
Is that good? 3:35, we're back. Excellent. Okay. See you soon. Ernest, we're good, buddy? I think we're on track,
I
right?
think we are. Yeah.
Right?
We're a
Good.
bit behind,
Okay,
but
okay. Well, yeah, but we had a lot up front. I think it's going to go a little quicker now.
yeah.
It'll be a little quicker.
Okay.
Beautiful. Okay, man. See you in a few minutes. All right. Is there anybody back already, or you guys back in the room yet? Maybe not. Well, Ernest is back.
Okay, should we start?
I think we should start. Is everyone back? Just making sure. It's funny, I only see Serene in the little box up top, but if you go to the participants, there's they're all there.
Yeah, I think it's because we didn't allow everyone to unmute.
Oh, right, good point. Oh my, good one. That's true. That's true. I wonder if we can do that. Oh yeah. Huh. Good point. Um, yeah. I mean, it's all, allowed to talk, asked to unmute. Oh, I get it. Yeah. Okay, well, I'll just allow
Okay,
everybody to talk. Yeah, there we go. Why not? I mean, obviously people would. Asked to unmute. Sorry, guys. For those of you that I'm asking to unmute, just ignore me. That's just because I was clicking the the wrong button. There we go. And then we get to see some reactions and stuff if we ask. There we go. Nice. I think that's everybody. We lost a few people over the break, but maybe they'll come back.
okay,
Let's get started.
awesome. So next part is about calibration. What we do here is just to see if the model is calibrated or not. We don't want to calibrate the model if it is not. There are different ways to do that, and I just briefly mentioned a couple of notes. So same scenario, same types of codes for data loading, etc., etc. Now this time, just to show the concept, we have a one-time random data splitting. Okay, so this is a 75-25 data splitting. We train the model, we get the AU log, and it is 0.93. Now, you should draw calibration plots to see how your model has learned the data. So the calibration plot we have is something like this. It's not a disaster. The fact that it flips below and above this diagonal line is a good thing. And whether this is acceptable for your case or not is a clinical question. There is no deterministic answer to that. However, we do know now that this model is not calibrated. There are different theories. Some people argue about them. However, general belief is that if your dataset is big enough, if your model is well trained, and if you use deep learning, those deep neural networks tend to be well calibrated. However, in my experience, it is not the case usually. So anyways, just do the calibration plot and see where you stand. Now, to calibrate this, after you know it is not calibrated, there are many different ways. One is to train another model to just map the predicted probabilities. One is to switch to models that by default learn to be calibrated. You can redesign your pipeline. There are many different ways. The only thing we wanted to show was how to identify if a model is already calibrated or not. So that's about calibration. Feel free to stop me and ask your questions. We move to confidence.
Actually, Ernest, I'll just make one little quick point for you guys when you're looking at it is under the line and over the line. So remember, on the line is perfect, which is fantastic. If you're below the line, it can indicate that your model is overconfident, and if it's above the line, it is underconfident. That's just kind of a rule of thumb for what you're looking for. And you want it on the line, right? You want it on the 45-degree angle. But you know, if your points, like in this case, these points across the probabilities from low probability up to 0.65 or something like that. Well, 0.65 is good, sorry. Let's say up to about 0.6 is that it is overconfident. Okay, and then the points that are above, it's a little underconfident. Does that make sense? Just to give a kind of a quick appreciation of what this plot's trying to tell you.
Thank you very much. So, moving to confidence. Confidence is a big topic. We can have dedicated lectures to this topic and talk about it for many conferences. Anyways, so there are multiple approaches to quantify how confident a model is. And again, there are slight variations of how different people even define confident. However, here we look at three approaches. One is based on the output probability. You can argue that output probability is not related to confidence. Input perturbation-based methods to enable confidence score reporting for your models, and also ensemble agreement. You may find different terminologies for these. For example, there is a method, it is a well-established method called ensemble deep learning, and EDL. EDL itself is a topic to enable this confidence score reporting, and there are many other ways. So I tried to make it into a simple to understand framework for you so that you can follow the ideas. Same data set, same loading codes as you can imagine. And this time, again, we have this random splitting, we get the AUROC, same thing as before we had. Now, we select one specific example. Okay, so here we are getting a random index to pinpoint one data example from the test set. Okay, so the index is 44, true label is 1, predicted label is 1, and now based on the predicted probability, you can say, well, if it is class 1, I have a predicted probability for this model, and if it is very close to 1 or very close to 0, it means that my model is confident that this specific example belongs to class 1 or class 0. But if it says 0.55, yes, I'm just thresholding the predicted probabilities to 0 and 1. However, the model is not confident. And if you search, there are papers out there. Some of them are very simple. There are one paper we had in the past was that how about making two thresholds? So instead of thresholding the predicted probabilities at 0.5 and map everything above it to 1, everything below it to 0, how about having two thresholds? Above the higher one, we say 1, below the lower one, we say 0, and in between, we say I don't know. So that's the idea for output probability-based methods. Then you can perturb or manipulate the input to your model and get the confidence. And this is how you usually derive your attention maps for techniques like RISE and LIME. So you have a classification model. Let's say it is an X-ray, and then you want to see where on the image derive the model to get that conclusion that this case is positive or negative, or whatever the classification label is. So there are different ways. GradCam, you may have heard about it, or different methods, but a class of those methods work on the input image. And the idea is that you just perturb it and see if your model can identify this is still from the same class. Now, the idea is very simple. So we repeat our experiments 100 times. We generate random noise, and then we add that noise to the base array we have. I'm still using the same example. And then we get inference. So 100 times with different noise, and this is the result we get. So baseline probability, you saw it already for that specific example. We had above 90. And then once you start perturbing, it also depends on how you perturb. Maybe the noise generation code I used was too harsh, or was not that accurate. There are techniques for that. You can learn this noise from your data set that will be a bit better. However, here I just wanted to show you the idea of perturbation, and then you get all these probabilities, and now you can determine or you can derive confidence scores based on the variation of these predicted probabilities. If always it says, hey, 0.8, 0.8, 0.8, yes, it is not above 0.9. However, it still is able to identify the predicted class correctly. However, if you get closer to 0.9 or even come lower than that, it means that your model is not confident. So that's kind of the overall idea. And finally, you have ensemble confidence. So with ensembling, you need to have more than one model. Here, what we do is that we keep the data splitting the same, because ideally in clinical settings, you don't want to mix everything with everything. You still want to be able to track your patients, as we discussed earlier. And here we define 10 different combinations for hyperparameters for our random forest classifiers. And then we train 10 different random forests based on those hyperparameters. So now I have 10 random forests. Inside, it's a little bit different. Maybe the number of trees are different, max depth, etc., etc. However, they've been trained to do the same thing based on the same data split. And now, for each patient, I can have 10 different predicted probabilities. Well, if you imagine, the rest is exactly like a perturbation method. You are converting one predicted probability to a bunch of them. And then based on the distribution, you decide if the model was confident or not. Again, this is not a comprehensive and generalizable definition of confidence. However, these are more technical approaches from machine learning point of view of how you can enable your models to give you some sort of confidence score as the output. The baseline here on this plot comes from that single model that we trained at the beginning. And then the rest are from 10 different models that we trained. As you can see, there is a bit of variation in predicted probabilities for that specific example. And based on this variation, now I can, for example, report the mean predicted probability as the inference, like the final predicted probability will be the mean of these 10. And then for confidence, I can report the confidence interval or range or whatever. Anyways, that is the whole idea. Any questions, any comments?
I don't see anything, Ernest. I think we're good to go. Just double checking. And nope, everybody's good.
Okay.
You pop your hand up if anybody has a question or whatever, or throw it in the chat, please.
Awesome. So last section for classification is about superiority. So the idea is that you have model A versus model B. Which one is better? This is very popular for doing research, especially in academia. All journals ask you to compare your models with some sort of baselines. Unfortunately, still, you see papers published with just one single shot. It happens a lot at competitions. I understand there is a bit of computational load concern in that regard. However, we should all know that then if you have one-time data splitting, one-time testing, it is random. It is random and it is not reproducible. So what we want to do is to have a statistical foundation to compare to the two models systematically. All right, so first for statistics, you need variability. So if you have one predicted performance level, let's say AUC of model A is 0.9, AUC of model B is 0.8. Well, there is no stats here. It's just two numbers against each other, and that's lack of statistics that we see in some of the publications and challenges. So to enable statistics, you need to have more numbers. And one way can be using data splitting, like repeat the experiments we already talked about. Here, we fix the tenfold evaluation for comparing two different models. Now, one thing to keep in mind is that if you fix the data splitting in a way that you use the same splits to evaluate model A and the same for model B, then you have a better chance to get a significant p-value. We'll talk about it in a minute. If not, for example, you are comparing your model with another group and they just say, we use this data set, we use tenfold data splitting, but they don't report the forwards. Well, you have no options. You can still compare these two, but your test cannot be paired anymore. And if it is not paired, it's harder, it's more conservative, and you have lower chance to get a significant p-value. So, okay, we use this 10-fold data splitting. We fix it using a seed, and now we train two models. From each fold, from testing experiment, we get one AUC. As I said, it can be any other metric. However, in this tutorial, we focus on AUC just because I love it. And so we have random forest versus extra trees. And we have these 10 two sets of 10 continuous numbers, different ways to compare them. At least you need to report your mean AUC for each group and standard deviation. If you want to conduct a more classical statistical test, there are different approaches. Some people blindly go for t-test. That's a bit wrong, I would say. It's not the best way you can do it. So what you can is to first conduct some normality test check. Here we use Shapiro. The null hypothesis for Shapiro is that your distribution is normal, your data is normally distributed. And now, if you get a significant p-value, it means it is not normal. Now, what you do is that you do the Shapiro. Here, the p-value is 0.1. So it is not significant. It means we can go for a parametric test like t-test, and we conduct the t-test, and then the p-value is not significant. So these two models, from the statistical point of view, are not that different. Okay, so this is one way you can do this. Another way you hear a lot in machine learning societies is bootstrapping. And bootstrapping, if you want to summarize it, it's just random sampling with replacement. Personally, I don't like it, but in many different scenarios, you don't really have any other options. If, for example, if your model is very heavy and you cannot afford the time or computational load to repeat your tests for like 10 times, well, one thing you can do is that you at least fix the test set for different algorithms or different models you have, and then randomly sample a subset of that test set, measure your performance level, for example, using AUC, and then keep the AUC for model A, keep the AUC for model 2 somewhere, go to the next next round, resample using that new sample, again, test this, go for a number of times, and then at the end, you have multiple AUCs to be compared with each other. So that's the idea of bootstrapping. You have the codes to do it. Here we are doing it. I'm setting n equals to 100 in this case. However, in many codes, you will see 1000. Well, Dr. Pascal should definitely comment on this. And in my opinion, it is one of those gray areas that you see, hey, I know what you're doing, but you cannot really reject something and say this is wrong, because let's say you have 100 examples dedicated to the test set, and then you set the number of repeats to 1000. It means that you will have repetition for some of the examples. Is that okay or not? Definitely it is okay, but I don't know any systematic way or established theory for setting the optimal n in these scenarios. In this case, we used a 10-fold cross-validation. So let's say we have 37 patients in each test set, and the number of repeats are set to 100. Well, we will overuse some of the examples for sure. Is it acceptable? Yes. I haven't seen any case, any journals that will reject you because of this, but just be careful. Two more comments, and then I will ask Dr. Pascal to give us some more advice. One is something that I learned from him, parametric versus non-parametric tests. If you can go for parametric tests like t-test, go for them because you have a better chance for getting a significant p-value. And in this one example, I'm showing the p-values from t-test and Mann-Whitney U. As you can see, Mann-Whitney has a higher p-value. So that's one. Paired versus unpaired, again, we discussed this. So same thing will happen. If you can somehow manage your context in a way that a paired test can be applied, use it, you will have a better chance of getting a significant p-value. Dr. Tyrell,
Yeah,
would you like?
that's great. Yeah, absolutely. That's great. And there are a few things that I can definitely touch on for sure. It'd be great to actually do a little poll of who's in the group, like who does what, who's done what in their publications, like or pushbacks from reviewers. I'd love to hear that. So if you guys want to share that in the chat, please do. I'm going to just share my screen again, if I may. So Ernest just talked about these scenarios, and I'm just going to touch on them just very quickly again. And so the one was the single train split, right, at the beginning, and then we have the k-fold cross-validation. So exactly what Ernest said. The k-fold is great for other purposes that we've already talked about, but definitely for statistics, it increases your numbers. So it increases variability, which is what you need, variance, right? Which is what you need for the analysis of variance, right? That's what we do in statistics. So if you don't have variability, then we can't work with it. And so that's what essentially your cross-validation is doing. In a five-fold, for instance, a five-fold cross-validation, you have five paired, comparisons, right? Because you do it 5 times. And so that now your n is equal to 5. So I'll just warn you guys a little bit about that as well. And that is, don't forget, we're using a t-test, Gossett, or Student's t-test. Student was his pen name, but Gossett was the statistician from Guinness, if you guys remember. That's he worked for Guinness, and he figured out that when he was sampling and testing his beer, his the batches of beer, that there was a problem with the tests, right? So that if you have very small samples, then the distributions would flatten, right? So exactly what Ernest said again is that when you're making a choice between Wilcoxon or like a non-parametric or a parametric test, in general, the advantage of non-parametric is you don't have the assumption of distributions, right? Like there's no requirement for the assumption of distributions, and therefore that's an advantage. But the disadvantage is they tend to be more conservative. So meaning that the test, it's harder to get a significant p-value in non-parametric analyses. And so if that's important to you to have a distributionless analysis, then they're well worth it. But if it is parametric, if it is a parametric comparison, so a t-test would apply, then definitely that would be the way to go. And I'm going to say offhand, that's probably the most common way oops, let me get, back to my screen here. The most common way that people use is the t-test, okay? So before I go to that one, there's one thing that Ernest didn't mention, which is just for you guys to know. When you do a single test, you can't do anything, right? Because you have a single split, you have a single test, you have one value, right? So what can you do? What can you do? Well, there is actually a little thing you can do, and that is, if you're really stuck and this is all you have, and you really want to get this published, and you need to, your reviewer is saying, hey, what the heck, right? Then you can look at your pairs, but in this case, we're looking at the predictions. Okay, so you can look at all, what's predicted and what's the truth, and you can do what's called a McNemar's test, and you're looking at the difference between discordant and concordant pairs. Okay, and that's a form of test, and you can report that as but based on your predictions. It is absolutely, you're desperate. Okay, like you are desperate here. If you're reporting this, every reviewer is going to say, bro, what are you doing? But you know what? I'm sharing it for you. This is what you signed up for today for, that is an option for you. Okay, so you can actually look at the predictions and just see how well the predictions match the truth using a McNamar's test, and you can provide a p-value that way and whatever. So is it fantastic? No, but I'm sharing it with you as a last ditch. What can I do? So when you're doing the k-fold validation, so Ernest just stepped you through this, right? So you do a pair t-test, you're comparing the pairs, that's wonderful. So the interesting thing is Ernest, then he goes on and he says that, doing the t-test, the problem with the t-test, right? There are problems with the t-test. And if you have a very small number, you're doing a t-test, which is good, right? That's appropriate, right? That's what you're supposed to be doing. But inevitably what happens is because it's not perfect, you breach one of the assumptions, and that is independence. The assumption of independence of your pairs, unfortunately, is breached because of the way the folds are being used, right? And so this results, unfortunately, in an inflation of the type 1 error. Okay, so that's the downside to this. But I'm going to say, and I can't wait if people are willing to share, this is probably the most common way of doing and reporting any statistics between models that I know of. As a reviewer, what I see, everybody does this. So it's kind of accepted, and it's the dirty little secret. Okay, and it is what it is, and that's fine. So what Ernest did, which is great, is he automatically went to tenfold, right? So that's much better. That's much better. Like, tenfold is much better than 5, because you now have 10, right? N of 10. So that's smarter. That's definitely, that will give you a better estimate. So that's good on Ernest, and so take that advice if you can. Okay. There is this test here. I'm showing it to you, but I don't expect anyone's going to use it because it's computationally heavy and a bit silly. And it was designed, somebody proposed this a long time ago, and it is a step up in terms of the ability. It's a 5 times 2 cross validation. No one's going to do it though. It's just kind of this flip-flop, right? And you do it 5 times. But it does provide a better estimate. So, but no one's going to do it because it's computationally heavy, and there's other reasons that it just doesn't, it's just not convenient. But just to be mindful, because you came here for statistics, this is an option for you as well. Now, the one he talked about was bootstrapping, which he's not a big fan of. That he's not the only one. There's many people that are not big fans of it. And the reason for it is because it's tricky to find the sweet spot. So exactly as you say, you got to hit saturation for your distribution, right? Because it's based on a distribution of possibilities. And so, for instance, if you do a 5-fold, the number of unique possibilities of 5 values, right? Because you have 5 pairs, 5 values, and then you're resampling from those 5 with replacement, correct? And you do that over and over and over and over. Well, there's only really 3,125 different possibilities. And so right here, I'll just put it right here for you guys. So that's the tricky bit, is do you have a full enough distribution is going to be the question. And then how many times do you have to sample? Most people do 5,000. That's kind of the accepted. And you just want to reach saturation. So why is bootstrapping interesting, or it is valid, by the way. It is a valid approach. Is it, why would you want to do it? Well, for one, you get confidence intervals, which is fantastic, right? And within the confidence interval, if you get 0, because don't forget this, it's a difference between your means, right? Or between your values, right? 0 is, means there's no difference, correct? And so if 0 is in your confidence limits, then there's no difference, right? And if it's outside of it anyway, so you get it. So the question then is, can you use it? Absolutely. So bootstrapping, if I go to the summary, overall bootstrapping is considered as strong, right? A strong value. I would say, actually, if you're really not sure, right? You can certainly do both. Right? You can report your paired t-test, right? And then bootstrap to get confidence, right? Which is nice. And your reviewers will appreciate that. So that's overall. The robust way that I showed you guys, I wouldn't bother. I would say most reviewers actually would say, "What's that?" Like no. But the reason I'm reporting it is just to give you this kind of idea of what's going on and what's possible. And then you choose. You guys are in charge, right? But the things definitely to not do is unpaired, which happens. People report as unpaired. It's just not appropriate. Okay. Once again, I always say not appropriate. I'm not saying it's wrong. It's just going to give you a really poor estimate. Like your estimate to the truth is going to be terrible. Okay, so don't do it. Go for what's appropriate, which is a paired t-test, and never just compare point estimates because that's silly. And I get that. I still get that when you read papers. They say, "Oh, this one's better than that one." Then literally they'll say 91 to 92%, and you're like, "And did you test that?" But it doesn't happen. Okay. The last thing. Do you want me to touch on this, Ernest, before we move on? I'm just going to do it really quick, and that is, what do you do if you have a continuous outcome? It's really easy. You do the same thing. Really, really you do. So if let's say you're working with MAE and you're predicting age or something like that, well, it absolutely is the same thing. If you have a single split, if you have a k-fold split, you're just going to take the difference and you're going to do your test, right? Wilcoxon, if you're worried about the having a distributionless test for sure is as Ernest showed, excellent. But essentially the approach is the same. So if you're worried that, oh my God, it might be different, it's not. It's essentially the same approach, and that's what you're going to do. And then, yeah, same thing for the k-fold, of course, sorry. And here's your summary, same thing, as I said, yeah. And that's it. Then we're into agreement. So there you go. Thank you, Ernest. Back to you, sir.
Thank you very much. Okay, so I already shared the link to the GitHub repository. It was requested in the chat. We covered everything here. I believe so. And yep, so ready to go to the next module, which is segmentation. So segmentation is another big chunk of AI applied to medical imaging and in general to medicine. For this, we are using a different dataset. It would take a long time to show you how to train models, and it would be absurd because we don't want to talk about training. It's not a machine learning basics tutorial. So what we have here in the dataset is ground truth segmentation labels from Brad's 2025 pediatrics cohort. And then we trained an NN unit model to do the same thing. And these are the inference segmentation masks from the NN unit. There is one catch, which is I wanted to keep everything super duper simplified for this workshop. So BRATS by default is a multi-region segmentation challenge, which means you have tumor core, you have edema, blah, blah. For this tutorial, we have converted BRATS into a whole tumor segmentation challenge, which means anything above 0, like we keep background, anything else is just foreground. So that's how you get to whole tumor challenge. It is much simpler, but it fulfills the requirements for this tutorial. And then we have one single image just to show you what the dataset was. And again, it is a multi-sequence MRI dataset, which means for each patient, we have 4 different MR sequences. However, what we are providing here for this single sample is T2 flare. So that's the data set. Let's get into the codes. Do we have any questions in the chat? Nothing. Okay.
Just checking. We're good.
Okay. So exploratory data analysis.
Excuse me, can you hear me?
Yes.
Yeah.
I've posted a couple of times, and I don't think you're seeing my questions. One was, can you post the title for the book that was recommended before the break? And then I also need the GitHub link.
I
Yeah,
already
sorry, I was just going to say they're both in the chat. Can you not see our chat?
I can't see anything in the chat right now. I can
Okay.
only see what I've posted.
Okay, so that's a bit
Actually, I
odd.
see it now. I see it
Oh.
now. Posted at 3:12. This is the
Yeah.
GitHub repo, and here's
Yeah,
the link.
yeah.
Great. Thank you. Got it.
Okay. No, great. Absolutely no problem.
Thank you. Thank you.
All right, so exploratory data analysis for segmentation. These are just the foundations we need to do the project. So I wanted to share a couple of technical notes with you. Recently, we participated in Brad's 2025 Pediatrics Challenge, and I thought these all would be very important. So again, importing everything, and then I ran these codes on my local computer, so I don't have that specific cell to make it working on Google Colab. Be careful of that. If you run the codes as they are on your Google Colab, you will get some errors. You need to copy this cell. And as I mentioned earlier, you need to fix your path. This should be the folder name you will choose to organize your Google Drive. But anyways, so that's the idea. In the ground truth and inference subdirectories under data, we have Nifty files. And each Nifty file is for one patient. It can be ground truth, whole tumor segmentation mask, which is binary, or inference. Now, we need some helper functions just to load Nifty files, etc., etc. One thing, it's not related to stats, but I wanted to highlight is that, of course, one of the first things you need to do is to plot some of these slices from your patients to see what's going on. When you plot, you still see this in many publications, especially in ML conferences. It's okay, but you may get rejection because of that. So pay close attention to the orientation of your data. On the right, you have axial view of a brain MR. In many ML papers, you see that is rotated by 90 degrees, which is not clinically acceptable. So that's note number one. Note number two, always overlay your segmentation masks to the base image. Don't plot the mask somewhere else, and then as a subplot, you provide also the image, because comparing the boundaries becomes impossible for the reviewers. Next thing is that overlay inferred and ground truth segmentation areas and boundaries on the same image. Here, we have ground truth in green and inference in orange. Don't make it too thick. 1 or 2 pixels are enough to show those boundaries, and that's all in terms of showing what you have. So this is one of the examples we have in the dataset. Now there's another concern, which is the EDA itself, exploratory data analysis itself. There are different things based on previous experience. We realized that not always regions of interest, let's say tumors, uh, are kept continuous. Like you don't, sometimes you have multiple islands, which means the ROI or VOI was partitioned. And this needs to be double checked by the clinical collaborators you have for your projects. Most of the times, again, based on my experience, it is not acceptable. So you need to pre-process your data and make sure if you're working with a focal disease, your region of interest or volume of interest is continuous. You cannot have islands. Anyway, so we have functions here to get the volume of tumors, to get number of islands, and to get the bounding box sizes. Also, we take into account voxel spacing in different directions, um, and bounding box size again in different directions. So that's the concept of EDA we have. We have the codes, we run the codes, we get all those stats and put them in a CSV file. And now you can start working with data visualization techniques to see what's going on. So first thing is on the left, you have number of islands in both ground truth segmentation mask and inference. You can see that even ground truth segmentation masks for this challenge were not continuous. We had islands. And as I said, it's because these days more and more people are using AI pipelines. So if you use a unit and just minimally revise the output of a unit to get your final segmentation mask, it means that you may have disconnected regions in your tumor. It's not real, but that's what happens. Also, if you do the segmentation prior to some pre-processing techniques, for example, if you want to first do the segmentation, then co-register your MR images to an atlas or something. So registration is one of the pre-processing techniques that may result in having some sort of disconnected and partitioned regions of interest. So that's one thing. Again, using the EDA results we had, you can also see the distribution of tumor volumes across patients, both for inferred and for ground truth segmentation masks. We will talk about other techniques to more closely analyze your results. However, this is a good starting point after you have trained your models, after you get inference for the test sets, just to analyze how your pipeline worked for those test cases. For example, one thing you can see here is that the distribution of inference and ground truth segmentation masks in terms of tumor volume are following each other. So we are fine, perhaps. And then for inference, my model tends to predict more connected subregions. However, ground truth masks I have are more partitioned. So in this case, using a post-processing, you can shrink your predicted masks based on, for example, voxel intensities, and that post-processing should help you get a higher performance. Anyway, so this is the EDA. We will use it in the next modules. We don't have that much time, so let's go to evaluation metrics. So we have the inference. We have those nifty files, predicted binary masks. And now the idea is to derive different evaluation metrics. Dr. Turrell will go through definitions of these metrics. We have many different categories. These are some high-level classifications. We have overlap-based metrics, distance-based metrics, detection or objection or object-level metrics, calibration, probabilistic, region volume, advanced and hybrid, multi-class, composite scores, etc., etc. The list goes on for forever. So what matters is that you provide some specific metrics so that you and anybody else who's reviewing your work is able to judge how the model performed. Now, if you're familiar with segmentation tasks, one of the good metrics and very popular is DICE. So that's one thing you can report. HD is another good one. It's a bit sensitive to outliers, so maybe HD95 you can use it instead. Anyway, so here we wanted to show you how you calculate those metrics, and these are all prior our main statistical analysis. So you get those metrics calculated and you save them somewhere. You also have your EDA results and you have saved them somewhere. So now you have a CSV file, something like this. Different columns give you either evaluation metrics like DICE, or they can give you pieces of information you got from EDA. Okay. And now, last thing is to conduct your actual statistical analysis, which you can be very creative. You can go for bland Altman plots. Here we are using absolute difference volume. And this is the plot you get, or you can just categorize, group your scores based on, for example, number of islands you have. One thing that surprised myself a bit for this study was that if you get the box plots for the group that have more than one islands, and the ones that have continuous predicted binary segmentation mask, you see that average dice score in those disjoint cases is a bit higher. You can also compare your performance metrics. NSD is something that we are using here. Again, you have continuous numbers, so you can go exactly through the same process. So normality test, and then you can go for Mann-Whitney U or t-test based on the normality. Before going back to Dr. Tyrell, I would like to show you one excellent resource you can have to be able to choose different metrics. He will go through this maybe. I just want to mention it so that we don't forget. This my-data.ca. This is an excellent website. This tree diagram is a masterpiece. It walks you over different methods, different statistical methods you can apply to different scenarios you face. Dr. Pascal, back to you.
Thank you, sir. I'm going to keep this. I want to make sure we leave a lot of time for questions and stuff like that. So, sorry, once I go through this, what's next, Ernest? Like, just to be mindful of time.
I have one quick notebook for regression.
Oh, yeah, right. Regression. Yeah, yeah. Perfect. Okay, so let me, sorry, let me just open my presentation again. There we go. Make sure you guys are seeing my presentation. Yeah, we're good, Ernest?
Something is coming up, but not yet.
Oh, yeah, it's funny. I'm in here for some reason too.
Okay, good.
Is it up? Yeah.
Yeah.
Oh, Zoom quit unexpectedly. Huh. Just a minute. Don't send. I don't know. There's some brief little boo-boo. But we're good, right?
Yes, we see two different questions.
Okay, good. I don't know. I just got this thing pop up saying, "Broom, Zoom quit unexpectedly." Okay, but we're good. Okay, let me just make sure. Let me get my Windows is closed. Let me just make sure I can see the questions and the chat and all that kind of stuff. I just want to make sure everyone's still around. I think we're good though, right? Here we are, participants. Yeah, I think we're good. Excellent. Okay, so sorry. Okay, so what am I talking about? I wanted to just briefly talk, I'm going to be very quick on this, and that is the concept of what we're talking about, segmentation. What are we trying to do, right? What do we want to compare? So as Ernest said, you have a mask, and you have an algorithm that has created the mask, and you have the truth, which is your radiologist or somebody that has actually hand drawn it or something like that, and you want to compare how well they overlap. So right there is going to help you in the decision of what you go with in terms of a metric. And so if you're looking at overlap, then you typically look at DICE or IOU. The intersection of union is a little stricter, so it penalizes more for error, and that's your choice. Or Jacquard is called Jacquard as well. So that is just a choice in your for you, whether you do DICE or whether you do IOU. It just depends on how more strict you would like to be for the complete overlap, right? So the most common, as Ernest said, is DICE. IOU a little less. And then HD, and I'll go over it after. HD is if you really are really interested in the boundaries, you want the boundaries to be the same, then definitely HD is the way to go. And as Ernest said, what you have to be cautious about is outliers and stuff like that. So the question though is, what are we looking at here? So when you compare two masks, right? What are you actually looking for? Well, you're looking for differences. So in a sense, you're looking for agreement. You're looking for error, okay? So I just wanted to bring this up for you guys because it's important, especially in what we do. So agreement is your measurement error, okay? And that's what we're looking at with a DICE score, okay? We're looking at what's different, right? And you're going to consider it error because the expert is the gold standard. And what your model is doing is the estimate, the prediction, and if it's not perfect, then it's erroneous. And so you're looking for measurement error, and that's what these measures are for. But the tricky bit is usually when you're doing this is because you want to identify something, and you're going to make potentially a diagnosis on that. So there's another term that's very often interchangeably used, and that's why I wanted to bring this up, because it's not true, and that is reliability. Okay, so the reliability is relating to the error between subjects, like the between subject variability. So not the measurement error, but the differences that would be observed between subjects. Okay, and so those are the two terms that you need to remember, is agreement and reliability. And so agreement, as I just said, is really just looking for error. So differences due to a measurement error, something that's, could actually be random, right? Could just be a random error that's being introduced into there. And so the ones that you want to look at, and I think Ernest will touch on a little bit, is Bland-Altman. And so what's called the standard error of measurement. This is what you would measure this type of agreement error in, and Bland-Altman. And I'm not going to go into detail because this is kind of above and beyond where we're going, but I just wanted to show you that that's what agreement's about. And then I'm sure most of you can say, oh, I recognize this, the ICC, the intra-class correlation coefficient. So this is what's used for when we want to measure reliability. And this is, how well can we tell patients apart, for instance, like, based on decision-making, based on classification, based on, disease, identification, okay? And the big difference is the formula is you have to, it's the variability that is between patients, subjects, sorry, divided by the between subjects and your error, right? Which is your measurement error. And so you can imagine if your measurement error is 0, there's no measurement error, then your relationship is going to be 1, right? So that's your reliability that's being affected by measurement error. And that's the reason I wanted to bring this up, is just don't lose sight of what comes down, the path. So what we're talking about today in masks is agreement, right? It's measurement error. But don't forget, it also makes up a part of reliability, okay? And I'm not going to go through the example because I want to make sure we get back to time. There we go. I'm not even going to go for the math because we just did that very quickly. Okay, here we go. So reliability, remember, it's for distinguishing, groups, patients, and then for agreement, it's when you want to do error, and that's what we're talking about today for DICE and IOU. And so let me get to that one. That's the key takeaways. Here we go. Now we're jumping right into this overlap-based metrics, which is the DICE and the IOU. The pixel level metrics, accuracy, precision, and recall, that's if you're dealing at the pixel level. I just wanted to bring that up because people still report that. People still work in that area. If you really want to work at the pixel to pixel level, you can actually report accuracy, precision, recall, etc., all you want. And those are what's called pixel level metrics. So you can certainly report those. Boundary-based metrics, as we just discussed, the Hausendorff distance, which is the HD. And then there's a whole bunch of others that we're just not going to touch on because there's too many of them. So you're going to say, well, what are those for? They're for specific conditions, applications, assumptions, and you should look them up, right? So it's in your area of research. They're going to be specific, prevalent in your area of research. But what we're talking about today is just high level in general. This is what's mostly reported is your DICE, your IOU, and your HD. Like literally, that's the most common. So I'm actually not going to go through this. I want to make sure we have time. This is just the math, and I'm not going to kill you guys with the math. But here, let's just talk about an overall. Okay, so you have your two overlap metrics, right? So DICE and IOU or Jacquard. And the strengths is interpretability. Like really, that's what it is, and that's why it's so widely used. The Jacquard, as I said, is a little bit strict, so people use less, and it penalizes small errors a lot more. And then this is either a strength or not. So here's a good one, and I was talking to Ernest about this earlier, and he goes, "Oh, we should talk about this, right?" So less sensitive to boundary differences. Is that good or bad? What do you guys think? Because here's a trick. Here's a tricky one that we come up against in the lab all the time. And that is I ask my expert to delineate a tumor, okay? And so they delineate the tumor. So I don't know if you guys have used these softwares, but very often in radiologic, softwares, when you either have to go point by point, right? So you put a point in, you put another point, it draws a line, you put another point, draws a line. And so what happens is it's not perfect. It's that they haven't actually took a mouse and drawn the line all the way around. So it's jagged, like the edges are a bit jagged. When you train using whatever, and then UNet or whatever you used, right? You get a nice estimate of the line and it's nice and smooth. So inevitably that's going to impact your overlap. But is that bad, or is it bad? Right? So that's just something to keep in mind. And so then if you're going to, depending on which measure you use, you're going to more or less be penalized by that, right? And so keep that in mind. So when you're choosing your metric, you can, make assumptions, all right? That fits more or less. So anyway, that would be nice too if you guys want to share that in the chat. If you've come across that, we definitely have come across that. That's a common thing for us, because asking experts to actually point by point delineate a tumor and stuff like that, sometimes they will and other times they won't. So that's definitely a consideration. And then what Ernest said, number of islands, number of, all that kind of stuff definitely makes a difference in terms of what's important to you. Is it the full volume? Is it just the boundary? You don't really care what's going on in the middle. You just want the boundary. All those things will help you determine which metric measure to use. Okay, let me go back to here, and I think I'm going to go back to you. Yeah, because the last slide is just everything we've just said. Yeah. So yes, remote sensing, sure, precision recall. Yeah, these are just kind of an overall, but really it's a personal flavor and preference. I mean, how about you, Ernest? What do you typically report with your segmentations?
Again, it depends. DICE for sure is always needed. If you don't report it, then the reviewers will come after you and say, "Hey, where's the DICE?" What I've learned is that I try to keep things comprehensive, because when you do a project, you move on to the next one, and you want to go back to the reviewers and address the issues. It takes forever to be able to get on board it again. You forget the details, especially if you work on multiple projects at the same time. So because of that, I try to keep the flags on. I capture all the metrics, put them somewhere. I don't report them up front. It's just DICE and maybe HD 95, and then if the reviewers ask, I always have the numbers in my pocket.
Yeah, agreed. Yeah, and I'm gonna share that is the process for us. I don't see anybody else sharing their experience, but feel free to do so. But absolutely, it really depends on your domain. like, where you work, what you do, and who's reading your papers, and what the expectations are. And even within the domain, depending on the journal you're submitting to, they may expect something different from another journal. That really, really is. And you're going to say, well, why is that? Why is statistics such a pain, right? And it's kind of funny. The definition, the purpose of statistics, right, is sharing, right, results. That's essentially it. Is statistics provides you the ability to share numeric results in such a way that they are interpretable. That's your job in statistics. And so it's interesting. You would think, oh, well, there's only one way. But that's not true, because it depends on who the reader is. Because remember, you're sharing your results so that they're interpretable. So the thing is who is listening? Who are you working with is a very important component. So the way you report your statistics, you'd think there's only one way, but there is not. It all depends on who's appreciating your work, who's trying to understand what you're doing, is going to determine how you report them and provide interpretation. Anyway, I just that comes up all the time, and people get so upset, because they're like, "Wow, there's only one way to do it." Well, it's not true. Anyway, Ernest, back to you, sir.
Awesome. So we're done with the segmentation part. In our code, we just save all the results to this results directory. So that's an extra module we had for segmentation. Moving to the last part, we want to talk a little bit about regression. And again, code data directories. Inside data, we have pickle files. So the predictive features, the ground truth labels, and the patient IDs are already prepared. All we need to do is to load them. But where did we get these from? So this is a new data set, another data set. This is the third one for today. It comes from a paper which was about natural language processing. It was published a few years ago. Good thing about it is that they made the dataset available. So you have the link to the paper. You can check it out. The idea is, again, binary classification. It's about stroke. And what we have for that classification as input is radiology reports. Now, we can go over the data set, and I can show you how we use it. However, what is more important is to know that to be able to create this context for regression, I've used a couple of different tricks. First, we don't use the reports as they are. We feed them into an LLM. It's a transformer. It's a better description than LLM. It's called clinical line former. It's in the category of BERT things if you're familiar with. Now, using those, we can get embeddings. So I have saved the embeddings, and that's how I created this X. Y is the binary label, and ID is just patient IDs. And in terms of counts, the dataset is imbalanced. So 14%-ish has acute ischemic stroke. The rest do not have that. And just for fun, I created a t-SNE representation to show you how it would work. You cannot see the plot here. You need to run it on your local computer on Google Colab. It doesn't work because I didn't run it on Colab. I had it on my own computer. But anyways, that's one part of the story. Now, how we get to regression, because this is, again, binary classification. So what I've done is that we discussed this. and we framed this as an anomaly detection pipeline. So let's say the dataset was heavily imbalanced. We had just a handful number of positive cases. In that case, you would go for something which is called anomaly detection, as most of you may already know. So the idea is that you train your model with just one class, and then anything that does not belong to that class later in your test becomes like an anomaly. How does it show up? So what we do here is that we create the data split in this way. We set aside all positive examples for tests. We randomly sample equal number of negative cases and set them as well for tests. So that's what we do. It's here. Okay, the rest of the data set is just negative examples, and we keep that for training. So in training, we have above 2,100 cases, all negative cases, and what we have are embeddings from clinical law enforcement. Now, for test, we have 864 cases, half is normal, half is anomaly. Good. Now, we train a variential autoencoder. It's a very simple architecture. It's a like a unit type thing, except we don't even have the skip connections, etc. It's a classical VAE. And we train it in the simplest way. So again, no hyperparameter tuning, no nothing. Adam Optimizer, we run it from NumPy, we train it for 4D epochs, and we just watch the loss over epochs, and we see that it is converging. So our model is learning how to reconstruct embeddings for radiology reports for normal cases. Good. Now, you can plot the training curve. We talked about this. And now we get to the regression part. Of course, as you can imagine, the output for this was already a vector, so it's not a classification anymore. And because we are reconstructing the input, one of the most appropriate loss functions would be MAE, which was used. And now we get MAE over all examples in the test set. So that's what we do. Now we get to the statistical tests. We have MAEs. Now let's check the distribution by label. As you can imagine, box plots are good candidates for this type of data visualization. So we have MAEs. I apply a bit of jitter to be able to show each point on the plots. And you see reconstruction MAE for test cohort for each of those two groups. So as you can imagine, it is not giving us a perfect separation. The MAEs are kind of overlapping. However, we do see that there is a different distribution for those two sub-cohorts, and the anomaly detection is giving us a higher MAE score for positive cases. Okay, so that's very compressed, I know, but good news is that you have access to all the codes, the whole data, and the whole idea. So what we put together very quickly and in a very compact form was an anomaly detection pipeline. It reconstructs the input. So expectation is that output is similar to the input. And because it was trained with normal cases, when you input something abnormal or from a different class, in this case, it was from the stroke class, what you get is different. So you get a worse reconstruction. And that worse reconstruction can be used for classification, for anomaly detection, as they say. The rest, you're already familiar. these MAEs, good news is that these are not like classification labels. These are like predicted probabilities. So we have some sort of continuous numbers. And in terms of statistics, we can apply different methods to this. What I've done is that, again, normality check, and then just getting the man with you based on these two groups. And I show that these two are statistically different, and we could imagine based on the box plots and based on the numbers, because the number of patients we had was not, it's not huge, it's not massive, but like 800 cases just for test is something that you may not see regularly in AI applied to medicine. So that's the concept of regression, statistical tests, anomaly detection, all those things in a very compact manner. And yeah, so thank you very much. It's the end of my hands-on section. Back to you, Dr.
Thank you, Ernest. Yeah, that was great. Yeah, there was a lot to take in today. There really was. And so, I think what we can share, what we intended to share, is to invite you to embrace statistics. I know that sounds really corny, right? But really, what it means is don't be afraid of it. Don't see it as as something you just have to do, but more see it as your way of exactly as you said is sharing your results and the interpretability of results. If you see it that way, it may be less onerous for you. That the reason you're doing this is to improve basically your knowledge translation. So meaning that people are going to appreciate your work and they're going to trust your work better than they did previously when you did not provide any measures of confidence or statistics. And I think that's the goal that we had today. Hopefully we were successful. I think at this point, probably we should open it up for questions. If you have any questions, no matter what, please, feel free to use the question and answer box, put them in the chat, or unmute and ask your questions. Would be most appreciated. How about that? Any questions? Was it really that clear? It was so clear.
So thank you very much for the tutorial. I think I joined mainly to learn how to teach the students on that, because when I raise like similar question to the students on the statistics, because right now most of them just learn machine learning, they just want high accuracy. When I try to emphasize the importance of statistics, they usually do not aware that much. So I really like your approach to sort of introduce this like in the class. So so one question I also have is like, given that there are lots of benchmark these days, would that be actually better that when people share data set or like have some sort of competitions and things, they also actually recommend let's say what's the statistics test to say which one is the best method? Because right now a lot of like studies, they just share data set, but then like everybody quote it. As you mentioned, like even like cross-validation or testing, they randomly use different portions. So it's becoming very difficult to compare.
Wow. That's a great question, great comment and great question. And I, inevitably you think, if you're in the space, you think of that often enough, right? And I'm going to come back to my opening statement, right? Which is, and I really do believe this, by the way, is that there's no wrong answer. It's really just an estimate, and you're doing your best to approach the truth as much as you can. So to answer your question, you're right. Wouldn't it be nice if there was a standard approach that should be followed? And I would say, and I hope we imparted that in this tutorial, that there are some standard approaches that need to be followed, but there isn't necessarily a fixed way of doing it. And it's unfortunately because, as we've always answered, and Ernest started off this answer, is that it truly does depend, right? So, and the tricky bit on that is how much data do you have? How heterogeneous is your data, that you're dealing with? How many folds is always a question of how much data you have. It comes back to that. How many, heterogeneity, what kind of, modeling are you dealing with? That kind of, all of that will determine, how you are able to report your findings, right? And so I'd love to be able to say, Rosa, that there's an easy way to do it, but I haven't come across it. Like, there is definitely standard approaches that you need to follow, and that's what we taught today. But I don't think we can necessarily lock them down. And if we do, unfortunately, what happens then is, then we're kind of saying that one way is wrong, right? Which I truly don't think is the case. And so probably what I would hope, happens is that there are more, accepted ways of doing things, that people are more comprehensive. That's my solution as a statistician. And when I'm reviewing, statistics papers and stuff like that, is I always look for groups that when they report their findings, that they're more comprehensive. So for instance, when Ernest was going over, bootstrapping, he said, it's not really my flavor, sure, and he's not the only one, right? But it would be nice if you did report, for instance, you did your paired t-test and you did some bootstrapping. That's just interesting. It's a little bit more comprehensive in terms of the answer, right? And reporting of your folds, reporting of a split, how you report all of that, I think provides the reader with what they want. Do you know what I mean? Like if you judge for the reader, you're going to miss the mark for many people, right? Because if you say, I know how I need to report this, you, the reader, need to accept that, that's a problem, Whereas if you say, hey, man, I appreciate that everybody has different opinions, let me report for you different ways for me to show you that I'm trustworthy, and I'm going to be completely transparent with my model to give you as much, as many indices, as many measurements as possible, so that you make the decision on if you believe my work. I think that's the best way I can answer it, because it's a
I
very
fully understand. So in short, it's like full list, everything we could think of, and then we just like put out there and share in the.
Yeah, okay. I'm not sure about everything, but more comprehensive. I think comprehensive. Like, find a sweet spot. You know what I mean? Like, you don't necessarily have to do everything, but definitely provide some options, for your reader is probably what I would recommend.
Thank you. That's cool.
Yeah. Great question.
How about this? I would say we need to have some sort of minimum requirements, but then we don't put a strict framework to follow these lines exactly as we say. Because it's a great question. I had a couple of examples where the journal was asking for comparing with another paper that didn't have any statistical analysis. It was just pure random numbers. And they said, hey, they use the same data set, they got these results, and yours is lower. So as long as there is some foundation, I'm fine. I don't care if they did paired versus non-paired or different tests, but as long as it is valid, it's fair.
Yeah. Yeah, no, good one. Then I'm laughing because that happens all the time.
Yeah, I know that few. I know that few.
Right?
So I think the issue of time by time is that we cannot reproduce what others have done.
Yes.
So let's say they report certain numbers, and if we follow certain statistical way to do it, we could not reproduce what they do. So I
Correct.
think that's the major challenge for some of the projects we are handling.
100%. That's yes, you've hit it right on, and that's the internal versus external validity. That it's yes, it's not reproducible, which is a problem because it's just so unique to how they did it, which is a trick. And I'll actually add in one more little thing, and that is we're dipping into this world of parameterization. You know, just so many parameters, right? Just such big complex models. Here's the tricky bit. If you don't have enough data, or you know, if you're challenged, you have what's called statistically equivalent signatures, which means that you can have a number of models that are all different, you know, the way that they're constructed and what, you know, how their parameters are weighted, but they all give you the same answer. So that's statistically equivalent signatures. And so we have to realize that is, you know, that comes down to a math and physics thing called an ill-posed problem, right? So meaning that you can't find the answer because there potentially could be an indefinite number of possible models that are all going to give you the same level. And I think unfortunately that's happening, right? So each group will come up with a model, will come up with about the same AUC or accuracy or whatever, and the same prediction and all that stuff. But actually what's inside the model is a little different. And the reason for that is because they don't have enough data. They don't have everything we talked about today. It's just, it is what it is. And so there's another problem for you, Rosa, right? Because, you know, repeating what they did, I mean, they actually are, you know, your model and the model you're comparing it to are actually different, even though they use the same data. Anyway, so there's a whole other area of interest. And that's why I think it's harsh when people actually think there's only one possible model. It's not true. I mean, maybe hypothetically it's true, but you know, in our world, it's not true. It's just so possible.
Yeah, I absolutely concur because like getting the same, getting the same output is like there are many different models that can like achieve the same thing given the same set of inputs and outputs. But I think right now you also mentioned about explainability a little bit and generalization and all those. I think ultimately it's like depends on the stakeholders' need. So what our clinical partners like feel more comfortable to use.
Yes, absolutely agreed. And we could do a whole workshop on explainability because that's great. That's a great topic, which is building more and more, right? And the requirement for us to express interpretability and explainability with our work is just getting more and more and more and more. And it's funny, we don't have that many tools, you know, in order to do it. It's still not an easy topic. But it's definitely going to be a requirement for FDA and for Health Canada in order to use these AI models in the healthcare system for sure is going to be explainability. So hot topic for sure. Okay, so we'll include links to the recordings in our GitHub. That's excellent. Oh yeah, right. Okay, so I think we're actually done. We're done for time, correct, Ernest? So unless anybody has a burning question, last question that they'd like to ask us, we can let you go back and enjoy the rest of the conference. I think most of you are in person in Atlanta. Hopefully you have nice weather. It's beautiful here in Toronto, where Ernest and I are. But please enjoy the rest of the conference.
Thank you, everyone. It was a pleasure.
Yeah. Thanks, everyone.
Thank you
so much.
Thank you.